We've been talking about properties of solutions, including in particular our colligative properties. So we've talked about vapor pressure lowering, we've talked about boiling point elevation, and freezing point depression. And we looked at calculating things like new freezing points and new boiling points if we know a concentration of our solution. Now, with our colligative properties, we can also use them to get information about unknown substances. In particular, we can use something like a freezing point depression or boiling point elevation to determine the molar mass of a substance. So freezing point depression, and you guys will do this in lab, freezing point depression can be used to find molar masses of unknown non-electrolyte solutes. This is done by dissolving a known mass of solute into a known mass of solvent. So we've got to know our masses. These are things we can measure very easily in the lab. And then we're going to measure the change in the freezing point. So we would set up an experiment, which again, you guys will do in lab, in which we take our solvent and we determine the freezing point. We then add the solute and we determine the new freezing point, and that's going to give us our change in temperature. From that change in temperature, we can then determine the concentration of the solution, because we would have our temperature change from our experiment. K is a constant. We know what solvent we're going to use, so we would have K. And we're using a non-electrolyte, so that means our I value is 1. So we can use our temperature change equation to figure out our concentration. Once we know the solution's concentration, we can determine the number of moles present in the solution using the definition of molality. We're talking about our concentration in molality. Molality is defined as moles of solute per kilogram of solvent. We would have that molality from our temperature change equation. We would know the kilograms of solvent because we have a known mass of solvent, which means we can solve for our solute moles. Once our solute moles are determined, we can calculate our molar mass using the definition of molar mass. Remember, molar mass is the grams of a substance per mole. We're finding the molar mass of the solute that we dissolved, so it's the grams of solute per moles of solute. So this particular method can only be used for unknowns that are non-electrolytes. The reason for this is that in order to use our temperature change equation, we need to know what I is. If we had an electrolyte and we don't know its identity, we don't know how many ions we have present. And if we don't know how many ions we have present, we can't determine our I value. Now, if our substance is unknown, it's very easy to identify if it's an electrolyte versus a non-electrolyte. We can run a test to see if it conducts electricity. If it's a non-electrolyte, we can use this method to identify its molar mass. And that molar mass is going to be important in determining its identity. First semester chemistry, you would have looked at determining empirical formulas. So maybe you did an experiment in which you determined what elements were present, you determined the empirical formula, and in order to get the molecular formula, you needed molar mass. But this is the experimental way that we find that molar mass, so we can get from an empirical formula to a molecular formula. So we'll look at an example of how we would do this. We've got a 1.684 gram sample of unknown non-electrolyte, and it's dissolved in 47.963 grams of camphor. The freezing point was determined to be 170.88 degrees Celsius. The freezing point of pure camphor is 179.82 degrees Celsius. And then we're given Kf of 37.7 degrees Celsius. Now, this problem is going to be broken down into each of our individual steps. You need to keep in mind when you're working homework or test problems or any other practice problems, they're not going to be broken down, but we're going to break it down here. But all of your other problems, you're going to solve the same series of steps. From our experiment, first thing we're going to do is determine our temperature change. So our temperature change is going to be the 179.82 minus 170.88, which is going to give me a temperature change of 8.94 degrees Celsius. So that is coming from the pure minus the solution. So my temperature has decreased by 8.94 degrees Celsius, going from my solvent to my solution. Once we've calculated that temperature change, we're going to use that temperature change to calculate the molality of the solution. So we're just plugging into our temperature change equation. So our temperature change was 8.94 degrees Celsius. We set that equal to K. We're told K is 37.7. And our I value is 1. So we're rearranging this equation to solve for our molality. And we're going to get a molality of 0.237. Now that molality tells me my moles of solute per kilogram of solvent. We're going to use that to figure out how many moles of solute are present in that solution. And so we're taking the definition of molality. So that's 0.237 moles per kilogram. And we're going to set it equal to the definition, which is going to be moles of my solute per kilogram of my solvent. So in this case, my unknown is my solute, the camphor is my solvent, and I've got 47.963 grams of it. So if I convert that to kilograms, that's 0.047963 kilograms. So we're going to take this equation and we're going to rearrange it now to solve for the moles. So what we're going to do is we've got to get that 0.47963 kilograms out of the bottom of my fraction. So we're going to multiply both sides by it. So when I do that, I'm able to cancel my kilograms and I get left with moles. And I'm going to end up with 0.0114 moles. Now, finally, we want our molar mass. So the molar mass of my solute equals moles of my solute, which is what we just determined. So molar mass is grams per mole. So it's grams of my solute. My solute was 1.684 grams divided by moles of my solute, 0.0114, which is going to give me a molar mass of 148 grams per mole. So here this broke it down in the individual steps. We take our experimental information and we use it to find our temperature change. From our temperature change, we're going to use our temperature change equation to solve for the concentration and molality. Once I know molality, I can use the molality and my solvent mass to figure out my solute moles. And once I know my solute moles, I can use the mass and moles to determine my molar mass. So our last problem here, we've got an aqueous solution containing 45.7 grams of an unknown molecular non-electrolyte compound in 345 grams of water. It was found to have a freezing point, so the solution freezing point is negative 2.9 degrees Celsius. We're asked to calculate the molar mass of this unknown compound. So my solution contains the unknown compound. That is my solute. It's in 345 grams of water. Water's my solvent. So just like we did in the previous problem where everything was broken down, we need to know our temperature change. So here's where we've got to know water. Water's freezing point is 0 degrees Celsius. So if we start at 0 and we're now at negative 2.9, my temperature change is 2.9 degrees Celsius. So using my temperature change equation, I'm plugging in my temperature change of 2.9 degrees Celsius. Our solvent's water, so we've got to go back and grab that K value for water that we had in previous exercises. And K's value is 1.86 degrees Celsius per mole times M times an I value of 1. So we're rearranging to solve for our molality. Which is going to give us a molality of 1.6 molal. We're using our molality to determine moles of our solute. So we're taking our moles of our solute divided by kilograms of our solvent. So our solvent is 345 grams, which is 0.345 kilograms. So rearranging our solute moles will be the 1.6 times 0.3450. So my solute moles are going to be 0.55 moles. So now determining my molar mass. It's going to be my mass of my solute, 45.7 grams, divided by the moles of my solute, 0.55 grams. So we get a molar mass of about 83 grams per mole. So here we have a very practical use of freezing point depression in a laboratory. We use this commonly. So again, if we had this unknown non-electrolyte and we're trying to figure out what it is, we generally don't want things sitting around that we don't know what they are. This is one of the tests we would do, is we would use freezing point depression in order to determine the molar mass. Once we had the molar mass, we could do further tests to figure out empirical formulas and then molecular formulas.